This section is on spanning trees. There's a fourth property that's going to start us off in this section. If a network has n number of vertices and m number of edges, then and sorry, this didn't upload right, I guess. That should say m is greater than or equal to n minus 1. I'm going to write that up here. So m is greater than or equal to n minus 1. We're just going to create two cases for us in just a second. The redundancy of the network is going to come from n. It's kind of like saying, if we were to put an m right here, so instead of m, we're going to say n minus 1. So two cases, if m equals n minus 1, so m equals m, then the network is a tree. If m is greater than n minus 1, so we're coming off the greater than or equal to part, so if it's greater than n minus 1, the network has circuits and is not a tree. So in other words, we have some extra edges that we need to get rid of so that the network can become a tree. A tree is going to be a network with zero redundancy, and a network with positive redundancy is not a tree. Okay, here's an example. Just looking at picture A right now, the network in picture A has n equals 8 vertices, so A through H, and m equals 8 edges. So there needs to be one less edge for this to be a tree. The redundancy of the network is r equals 1, and remember that's from r is m minus n minus 1. So if we do that, 8 minus 1, because we have 8 edges and 8 vertices, that's 8 minus 7, which is just 1. So to find a spanning tree, we will have to discard one of the edges. So 5 of these edges are bridges of the network, and they will have to be part of any spanning tree. The other 3 edges, and they're labeled here on parts B, C, and D, so if you look at BC, that's not a bridge, because if we were to take it away, let's see, BC right here, if we were to take that away, the network is still connected. Notice also if we were to take away GC, the network is still connected. Same thing goes for BG. So these 3 parts that are part of a little circuit here, and I'll draw that on part A, that's what's causing this to not be a tree. So if we exclude any of the 3 edges, we will have a spanning tree. We just have to pick one of them. So given the fact that we can choose any one of those 3, we're going to say this network has 3 different spanning trees, as you can see in parts B, C, and D. Now write a different example. So how many spanning trees are in this figure? First of all, let's just look at the number of vertices and edges really quick. So the number of edges is 1, 2, 3, 4, 5, 6, 7, 8. So we have 9 edges, and vertices we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So kind of like the last problem, so R is going to be m minus n minus 1, and that means we have 9 minus 1, so 9 minus 8 equals 1. So basically in this picture we have one extra edge that we can get rid of. That's our redundancy. So if we were to take one of the edges away from the circuit, that would make this graph a tree. Notice here the circuit. So our 3 edges that we can pick from are C, E, E, F, or F, C. So notice if I were to take away, CE, we would have a spanning tree. We don't have any more circuits left. There we go. Or if we were to take away CF, okay, our network would now be a tree. Or if we were to take away EF, we would now have a tree. There are no circuits left. So our answer to this question is going to be 3 spanning trees. Another example here. So how many spanning trees are in this figure? Let's see it once again. We have 1, 2, 3, 4, 5. So this time n equals 5 and m equals 1, 2, 3, 4. Same thing. So similar problem. So remember, redundancy is m minus n minus 1. So 5 minus 5 minus 1, 5 minus 4, so 1. So basically all we have to do to create any kind of spanning tree is to remove one of the extra edges. And as you can see, the circuit here is BCD. So this is the problem. We have to remove one of those edges. So if we were to just get rid of BD, okay, all the vertices are still part of the network, and we have a tree, so that works. If we were to get rid of CD, all the vertices are connected, and we have a tree, no circuits, so that works. That's the second option. And then the third option is to get rid of BC. Okay, everything's still connected, and we have a tree. So the answer to that question, just like the last one, is 3. Okay, last example on here. Can you create a minimum spanning tree? So the goal here is to create a tree that has the least amount of total weight on the end. Notice that this time we have weighted edges. I'm going to do a quick example here for you just to help you get started. Let's say I want to connect these, maybe these guys. How about them? We'll have to connect this at some point. And we need this and alright, the only thing we really can't connect here is D and F because that will create a circuit, but I could do D to E, and there's a tree. Now this is probably not the minimum spanning tree because I've selected some of the larger values on the outside, so on your own I'd like to see if you can create a better tree that's going to have the least amount of weight in the end, and we'll discuss this more in class and see what y'all got.